This is the story of Mars's rebirth, a tale of ambition, engineering marvel, and the indomitable human spirit. In the year 2040, Earth's greatest minds and most daring explorers have set their sights on transforming the red planet into a world capable of sustaining life. The project, known as Ares Genesis, is not just about survival, it is a statement of humanity's desire to extend its reach beyond its birth world. Here we chronicle the meticulous process of terraforming Mars, the establishment of self-sustaining colonies, and the gradual evolution of an environment that once was barren into one teeming with the promise of life. Earth had long since outgrown its limitations. Climate change, resource depletion, and overpopulation had driven nations to look skyward. In a historic moment of unity, a coalition of governments, private enterprises, and scientific institutions came together to initiate the Ares Genesis project. In a televised address on a cool spring morning in 2035, the world witnessed the birth of a vision. We will make Mars a second home, a beacon of hope for generations to come. Preparations began with the launch of a series of orbital satellites designed to study Mars's atmosphere in unprecedented detail. These probes mapped the distribution of carbon dioxide, water ice, and trace elements. Engineers and scientists debated the best method to kickstart a warming process on a planet that had for millennia been a frozen desert. The consensus emerged to build massive orbital reflectors, mirrors that would focus sunlight onto the Martian surface, thereby increasing its temperature bit by bit. In addition, robotic missions were dispatched to deposit engineered greenhouse gases into the thin atmosphere. By introducing compounds such as perfluorocarbons, which are thousands of times more effective than carbon dioxide at trapping heat, the plan was to create a self-sustaining greenhouse effect. In the early months of 2040, as the reflectors unfurled in orbit, the first subtle changes were observed. Temperatures in certain equatorial regions began to rise. The once perpetual frost started to recede and the first traces of transient water vapor appeared in the atmosphere. It was a slow, deliberate process, measured in degrees and percentages. A 2% increase here, a 5% boost there. Every fraction of change was celebrated as a step toward a more hospitable world. As Mars warmed, a flurry of activity took place both on the surface and in orbit. The reflectors, each spanning nearly 500 meters in diameter, were positioned with extraordinary precision. They rotated gently to track the sun, ensuring that the maximum amount of energy was directed toward the targeted regions. Over a period of 6 months, the reflectors increased the effective solar irradiance by nearly 20% in select zones. This deliberate heating was enough to release trapped carbon dioxide from the polar ice caps, thickening the atmosphere further. At the same time, a fleet of autonomous rovers and drones began the deployment of greenhouse gas canisters across vast desert plains. These canisters, preloaded with a proprietary blend of gases, were strategically released in patterns designed to maximize atmospheric retention. In the grand scheme of terraforming, every action was interdependent. The warming provided by the reflectors triggered the release of carbon dioxide, which in turn amplified the greenhouse effect, further warming the planet, a positive feedback loop set in motion by human ingenuity. Beneath the surface, subterranean operations were underway. Robotic drills and excavators carved out vast networks of tunnels and caverns where volatile compounds were stored and later released in controlled bursts. Engineers had developed a pulsed release system. By intermittently heating the tunnels, they could force trapped gases into the atmosphere in rhythmic cycles. This process, though seemingly modest, was calibrated to mimic the natural warming cycles of Earth's ancient past, preparing Mars's surface for a future that could eventually support life. Every decision was data-driven. Satellite imagery, thermal sensors, and atmospheric spectrometers relayed continuous streams of information to mission control on Earth. Teams of scientists in deep underground bunkers and in high-tech laboratories analyzed the data in real time, making minute adjustments to reflectors' angles and gas release schedules. They marveled at the unfolding transformation, aware that they were witnessing the birth of a new world, a process that, though gradual, was irreversible. By mid-2040, As atmospheric pressure slowly increased and the surface warmed to near freezing temperatures, the first human settlers began their descent onto Mars. These pioneers were not mere tourists, they were scientists, engineers, and visionaries tasked with establishing the initial habitats that would later evolve into thriving cities. The first colony, designated Elysium Base, was erected in a region once known as the Arcadia Planitia. Here, a series of modular inflatable domes were installed on a carefully leveled plateau. Inside the domes, artificial ecosystems sprang to life. Hydroponic farms grew leafy greens and tubers, while water recycling systems ensured that every drop was conserved and reused. The domes themselves were marvels of engineering, constructed from ultra-thin, self-healing materials that could withstand temperature fluctuations and the relentless onslaught of cosmic radiation. Each dome was connected by pressurized walkways, forming a network that allowed colonists to move freely while remaining protected from the harsh Martian environment. The establishment of Elysium Base was a testament to human resilience. Every structure, from the central command hub to the individual living quarters, was designed with redundancy in mind. Backup systems, powered by nuclear fusion reactors and solar arrays, ensured that life support, communications, and climate control would never be compromised. The base's central command room featured a vast digital map of Mars, displaying real-time data on atmospheric conditions, resource extraction sites, and the progress of the terraforming efforts. One of the colony's most ambitious projects was the Green Arch, an experimental biodome designed to simulate Earth's diverse biomes. Inside the dome, engineers had recreated miniature versions of forests, wetlands, and grasslands. Native Martian soil, enriched with specially engineered microorganisms, served as the foundation for this artificial ecosystem. Scientists monitored the growth of algae and lichen, the first living organisms to colonize the biodome's surface. These pioneers of life were expected to pave the way for more complex organisms in the coming decades. For the colonists, every day was a blend of routine tasks and groundbreaking discoveries. Morning briefings in the command hub reviewed atmospheric readings and greenhouse gas release statistics. Engineers adjusted the orbital mirrors from remote terminals, fine-tuning their angles to optimize the warming effect. In the biodome, botanists carefully documented the growth rates of various plant species, comparing them to baseline measurements taken during earlier test phases. The spirit of collaboration was palpable, as experts from every field worked together to ensure that the delicate balance of Mars's emerging ecosystem was maintained. At the heart of Mars's terraforming lay a confluence of advanced technologies. The orbital reflectors, greenhouse gas canisters, and subterranean gas release systems were only the beginning. As the project progressed, teams of engineers and scientists developed a series of breakthroughs that would accelerate the process. One of the most revolutionary innovations was the bioregenerator. This complex system combined genetic engineering and nanotechnology to create organisms capable of thriving in the harsh Martian environment. Modified cyanobacteria, for instance, were designed to perform photosynthesis under lower light conditions and convert the abundant carbon dioxide into oxygen. These engineered microbes were released into the biodomes and even directly onto the Martian surface. Within weeks, swaths of the barren soil began to take on a greenish hue, a subtle indication that life was taking root. Simultaneously, a fleet of autonomous terraformers was dispatched to construct vast, shallow reservoirs and aquifers. These machines, shaped like giant mechanical beetles, dug into the Martian regolith and extracted water ice from beneath the surface. Once melted and purified, the water was stored in enormous cisterns and distributed via an intricate network of pipelines. The first successful test of this system saw a reservoir filled with nearly 10,000 cubic meters of water, enough to sustain the early hydroponic farms at Elysium Base. Another crucial component of the terraforming process was the solar shroud, a network of ultra-lightweight spaceborne solar collectors that doubled as protective screens. Suspended in orbit above key regions, these shrouds filtered harmful radiation while channeling additional sunlight to the surface. Their reflective surfaces were adjustable, allowing mission controllers to modulate the intensity of light reaching specific areas. This controlled illumination was vital for maintaining optimal conditions for the budding ecosystems, especially during periods when Mars's natural orbital variations threatened to disrupt the warming cycle. All of these systems were linked by an advanced artificial intelligence network, codenamed Prometheus. Prometheus was tasked with assimilating vast amounts of data from satellites, rovers, and ground-based sensors. It continuously optimized the terraforming parameters, ensuring that the delicate interplay between warming, atmospheric thickening, and water distribution was maintained. When anomalies were detected, such as an unexpected drop in local temperature or a malfunctioning gas canister, Prometheus alerted human overseers and initiated corrective protocols within seconds. This fusion of human expertise and machine precision allowed the terraforming process to proceed with remarkable efficiency. Yet, for all its technological marvels, the project was not without its challenges. The Martian dust storms, notorious for their ferocity, occasionally disrupted the delicate balance of the nascent ecosystem. Engineers had to design redundant systems and emergency protocols to protect the orbital reflectors and biodomes from the abrasive sands. Meanwhile, the relentless cosmic radiation posed long-term risks to both electronic systems and biological life. Shielding measures were continuously improved and new materials were developed that could absorb or deflect high-energy particles. Every challenge was met with ingenuity, and each setback became an opportunity to refine the process. As the terraforming efforts advanced, Mars slowly transformed from a desolate world into a canvas of possibility. The colonists, initially a small cadre of pioneers, began to grow in number. By late 2040, Elysium Base had evolved into a bustling settlement with over 1,200 inhabitants. Families, scientists, engineers, and artists all converged in this pioneering outpost, united by a common purpose: to build a new civilization from scratch. Daily life on Mars was a blend of routine and wonder. Early morning was marked by a chorus of automated alerts, the gentle hum of life support systems, the soft beeps of communication networks, and the rhythmic rotation of habitat modules designed to simulate Earth's gravity. Within the protective confines of the domes, children played in corridors that doubled as educational exhibits, where holographic displays taught them about Martian geology, climate science, and the history of Earth's own environmental challenges. In communal meeting halls, elders recounted the early struggles of the terraforming mission. They spoke of the skepticism that had once greeted the project, of doubts voiced in the halls of power and boardrooms across Earth. But here on Mars, where the ground was slowly being transformed into a living, breathing entity, hope was palpable. It was a hope that was built not only on scientific breakthroughs and engineering feats, but on the collective determination of a people who believed that even the harshest conditions could be overcome. Public works projects became a central feature of Martian society. Large-scale initiatives, such as the construction of a central biosphere arc, a vast dome designed to encapsulate a fully self-sustaining ecosystem, provided employment and a sense of shared destiny. Under the guidance of Prometheus and human engineers, massive robotic assemblers began erecting the framework for the ark. This structure, intended to be the first fully naturalized region on Mars, would house a microcosm of Earth's diverse biomes, from tropical rainforests to temperate grasslands, all under one protective canopy. The colonists also grappled with questions of governance, ethics, and identity. How should decisions be made on a world so far removed from Earth's political systems? In response, a new form of governance emerged, a council composed of representatives from scientific, technical, and cultural communities. Their deliberations, conducted in a combination of virtual forums and face-to-face assemblies, focused on everything from resource allocation to environmental preservation. These discussions were not only pragmatic but imbued with a philosophical determination to honor the legacy of Earth while forging a distinct Martian identity. Art and culture flourished as well. With fewer distractions and the stark, awe-inspiring beauty of a transforming planet as their backdrop, many colonists turned to creative expression. Poets, Painters and musicians found inspiration in the interplay of red dust and the soft glow of a distant sun, capturing the tension between what was lost on Earth and what could be achieved on Mars. This cultural renaissance became a vital part of the project's narrative, a reminder that terraforming was not merely a technical challenge but a profound human adventure. By the autumn of 2040, Mars had begun to display signs of a true atmosphere. Infrared sensors detected increased levels of oxygen and nitrogen in the lower atmosphere, and sporadic rainfall had been recorded in localized regions near the equator. The successful deployment of the bioregenerator had yielded its first major breakthrough. Genetically engineered algae and cyanobacteria were flourishing in the controlled environments of the biodomes, and their proliferation signaled that a self-sustaining biosphere might soon be within reach. A particularly dramatic moment came when a massive, artificially induced storm, triggered by a coordinated release of water vapor and greenhouse gases, swept across the newly formed basins. Observers at Elysium Base watched as dark clouds gathered over a sprawling region in the Valles Marineris. Within hours, gentle rains began to fall, watering the soil that had, until that moment, remained stubbornly arid. It was as if Mars itself were taking its first tentative breath, a symbolic event that united the colonists in celebration and awe. On the ground, teams of researchers hurried to record every detail of the event. High-definition cameras, environmental sensors, and drone swarms captured the transformation in real time. The data confirmed what many had hoped for: a measurable increase in humidity, a stabilization of surface temperatures, and, most importantly, a detectable rise in the oxygen levels of the atmosphere. It was a turning point, one that spurred renewed optimism and a flurry of activity as plans for the next phase of terraforming were fast-tracked. As the year drew to a close, the people of Mars found themselves on the cusp of a new era. The once barren, rust-colored landscape was gradually transforming into a world that bore the faint but unmistakable signs of life. The orbital reflectors continued their steady rotation, the subterranean gas releases maintained a controlled warming cycle, and Prometheus, the silent, omnipresent intelligence, ensured that every system operated in perfect harmony. Plans were already underway for the next stage, expanding the network of biodomes and integrating the growing naturalized regions with the human settlements. Architects and engineers envisioned cities that would eventually blend seamlessly with the Martian environment, where glass and steel structures would coexist with sprawling green parks and meandering water channels. The long-term goal was nothing short of audacious: a planet where humans could live, work, and thrive in an environment once thought inhospitable. Communication with Earth, though delayed by several minutes, remained constant and vital. Regular updates on the terraforming progress were broadcast worldwide, inspiring millions back on Earth who saw in Mars a symbol of hope and renewal. The colonists, in turn, maintained a deep connection with their home planet through digital archives, interplanetary video conferences, and even cultural exchanges that celebrated the heritage of Earth while forging a unique Martian identity. The legacy of 2040 was not only in the scientific and engineering breakthroughs, but in the spirit of collaboration that had defined the project. Every success, every setback, and every moment of awe had been shared by a global community united by the belief that humanity's future was not confined to Earth's fragile surface. As the first Martian rains nourished the soil and the first fully grown trees began to take root in experimental orchards, the people of Mars knew that they were witnessing history, a gradual metamorphosis that would one day turn a barren planet into a vibrant living world. In the twilight hours of that transformative year, as the twin moons of Mars cast their gentle light over the evolving landscapes, a quiet determination settled over Elysium Base. The challenges were far from over and the work ahead would be immense. Yet every colonist, from the seasoned scientist to the curious child, understood that they were part of something greater, a grand experiment in the art of planetary rebirth. Their legacy would not only be measured in data points or structural blueprints, but in the rebirth of a world that had once been condemned to desolation. As Mars approached the threshold of a fully self-sustaining biosphere, the people of the Red Planet looked to the future with cautious optimism. The terraforming mission had proven that through ingenuity, cooperation, and unyielding determination, even the most formidable challenges could be overcome. The achievements of 2040 would serve as the foundation for decades of further innovation, an ongoing journey toward transforming Mars into a second home for humanity. In the halls of the Martian Council, where decisions affecting millions were debated with passion and precision, a new motto was adopted: from desolation, life; from scarcity, abundance. These words encapsulated the collective spirit of the project, a testament to the belief that every setback was merely a stepping stone toward a brighter future. As engineers refined the atmospheric models and biologists continued to nurture the pioneering flora and fauna, the dream of a green, vibrant Mars no longer seemed distant. The story of Mars in 2040 is one of transformation on every level, the transformation of a planet, of technology, and of the human heart. It is a reminder that progress is not measured solely by the passage of time, but by the leaps of faith we take in pursuit of a better tomorrow. And as the first Martian year drew to a close, the people of Mars, standing beneath an ever-changing sky, knew that they were the custodians of a new era. A future where the seeds of Earth's legacy would blossom in the red dust of Mars.